Okay. Okay, I hope you can see everything what I can see from the screen. Okay, so in the last class, we talk about the solubility. It's one of the very important things in the chapter 4, working in solution. So we introduced some solubility rules, so you can use them to judge if a compound will be soluble in water or not. I already posted this one on Canvas. So let's review this knowledge. Yeah, I know it's boring to repeat the old things, but I think we will use this knowledge in this class. All the group 1 elements, when they form the compound, ionic compound, they are soluble. So if I will check the alkaline metal ions. If I see lithium, iron, sodium, potassium, for example, okay, it's soluble, and also ammonia. Ammonia is not group 1, but it's behaves very similar like group 1 in terms of the solubility. All ammonium salt are soluble. Okay, then we can look at another side, the iodine. So all the nitrate are soluble, and also these one are soluble. So as long as you see these things, they are soluble. Now, let's continue. The halide are also soluble, but you have to memorize some exceptions. For example, you see halide. As long as halide is not combined with these things, they will be soluble. However, if the halide combined with silver, for example, silver chloride, is not soluble. Yeah, similarly like sulfate are soluble, but there are more exceptions here. Okay, I think in the next week I will, from Monday to Friday, I will give you lots of in-class practice. I also will print out this one for you. So, okay, these are the rules. Most of other ions like phosphate, carbonate, chromate, sulfide, they are insoluble. Of course, there are some exceptions because we talk about that. All the alkaline metal ion and ammonia are soluble. This is we talk about that. So even these are insoluble, but when they combine with these two groups, they become soluble. Okay. So hydroxide salt are also insoluble. Again, these are soluble. There's no always soluble. And also, these are also exceptions. Okay, let's go back to PowerPoint. Yeah, I just want to let you know. And let me see. Can I move somewhere here? Yeah. So the solubility is a relative concept. What I mean is there's no, clear line. For example, this line on the left are soluble, on the right are insoluble. It's not like that, because solubility is gradually increasing, for different compounds. It depends on the application. What do you think is soluble or not? But one I searched from the internet, one judge is, at least some people say, okay, if one compound, the solubility is less than 0.1 gram per 100 milliliter, we think that is insoluble. Yeah, but that is not a universal criteria. Yeah, depends on your application. Yeah, how to say, if you say 0.0999, you think they are insoluble. But if it's 0.11, you think it's soluble. It's not fair because the difference is very small. This is why I said it's a relative concept. Yeah, you should keep that in mind. Yeah. But don't worry, in our test, we only test you something obvious. Yeah, if it's insoluble, it will definitely, you can see some precipitate and it's very insoluble. If it's soluble, it will be totally soluble. So we will not test you something sitting between. Yeah. Okay, I'll bring this back. You know, in the last class, we did some in-class practice. For example, if we combine this one and they form the soluble, there's no insoluble things will form. Yeah. Let's continue. This time, let's work on this. Forget about this three. If this one combined with this compound, how many insoluble precipitate can be formed? Let's check one by one. Use the rules I showed you at the beginning of this class. For example, if this one combined with this one, I think there will be no insoluble compound formed because this sodium, you know, and the potassium, they are both group 1 elements. Whatever, I mean, the anion is, it will be soluble anyway. So forget about these two. Now let's use this one to combine with this one. Now, sodium nitrate is also soluble because all the sodium compounds are soluble. We talk about that. The only things we need to check is the barium phosphate. You know, according to the rules I read for you at the beginning of this class, so all the phosphate are insoluble, except for some exceptions like the group 1 and the ammonia. But this one apparently is not any exception for phosphate. So, okay, in short, barium's phosphate is insoluble. Okay, that's one already. Similarly, copper phosphate is also insoluble, and silver phosphate also insoluble. So in this case, there are 3 insoluble precipitate, yeah, will be formed. So if you have questions, yeah, please come to my office, or we can talk about more. So from here, we will introduce different type of the reaction in solution. Before doing that, the first term is precipitate. So what is this word mean? This precipitate mean are insoluble solid compound formed during a chemical reaction in solution. Yeah, in other words, the precipitate is a kind of insoluble compound formed from a chemical reaction in solution. So when we have this type of things take place, we call that reaction precipitation reaction. Some people also call it exchange or double replacement. We will see. I will show you why it gets so many this kind of a name in the next slide. Example is if there are 2 solutions are mixed, for example, let's nitrate and potassium iodide. If we mix these 2.
In the test tube, we have an aqueous solution containing iron 3 ions. To this, we will add a solution of sodium hydroxide. A precipitation reaction occurs that produces iron hydroxide, an insoluble metal compound.
Yeah, this nice video showed you what the precipitate looks like. The examples like this. For example, if you have ions and you add some hydroxide ion, you see they form this kind of the brown color iron hydroxide precipitate. This is what we call a precipitate. So these reactions are also called a precipitation reaction. Let's take a look at more examples. The precipitation reaction is kind of a reaction that results in the formation of the insoluble product. In this case, it would be silver chloride. It's a video can play. I think this video is, there's no sound, but you can look at this formed precipitate is a silver chloride, you see. As I said, in this class, we will not test you some solubility questions, unclear. Yeah, we will only test you something very clear, like this. Human eyes can see it. Yeah, there's no doubt. It's kind of the insoluble compound formed. So here I introduce two kinds of equation. One is called molecular equation, another is ionic equation. So if you look at this equation, you should be familiar about that because we talk about the balanced chemical equation, right, in the last class. So that's just a chemical equation, but we add something like a state symbol, use a parenthesis, to indicate, okay, this compound is dissolved in water or soluble in water. That compound can dissociate into ions. Yeah, same here. And also same here, it's soluble according to the solubility rules we learned. But this we use the state symbol S mean solid. Yeah, that means some insoluble precipitate form is this one, insoluble. So this we give them a name, molecular equation or molecular total equation. Because you see every one compound is written in the molecular form. Because this is molecular formula and this is molecular formula. And this is molecular formula. It's not in the form of ions, I mean. Let's take a look at another one, ionic equation, what it looks like. The same reaction, because this one, like I said, the AQ here means this one dissolved in the water is soluble, and that compound will dissociate into these two types of ions. Yeah, this one will dissociate. Only when you have the AQ in the parentheses, this compound can be written this way, separate. Yeah. Similarly, like the potassium iodide, its state symbol is also AQ, means it's soluble and can dissociate into ions in the solution. So you may pay attention to see here, the two here, so I add two here, and that means this one molecules will form one potassium ions, but you have two of these molecules, so you will have two potassium ions, and you have two iodide ions, right? Yeah. But here, you have only one lead ions here, but you have two nitrate ions. These two mean you have two nitrate ions. This is why I put two here. We don't have to write down two here. We should write down here because that tells you you have two nitrate ions. If you write down two here as a subscript, that means you are talking about these two ions. It's one identity. It's one unit. Yeah, it's not separate. That's not true. Actually, in water, you have two independent nitrate ions. This is why we write down these two here, not as a subscript. So, and for product part, we continue this one. Yeah, I use arrow because there's no space. We can write down in one line, so I do it this way. So this one, we cannot separate them into ions because they are stay in the solid form, as indicated by the S here. They stay in the solid form, like the precipitate that we said, yeah. So they will not dissociate into ions in solution. So keep them, yeah. And this one, again, we end up with AQ because this is soluble in water and so can dissociate into the 2 potassium ion and 2 nitrate ion. So this equation, we give them a name called ionic, or not a name, complete ionic equation. It's understandable because the whole equation, you see, as long as they are soluble in water, as long as they can dissociate into ions in solution, for that type of compound, we wrote them in the form of ions. You see, ions, 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 except for something, you know, they don't dissociate into ions. We should respect, yeah. We should keep their in the molecular formula, yeah. This is reality, you know, we cannot do something, yeah. We just keep it there. So this one is called an ionic equation. So when we look at that ionic equation, let's check, yeah. For example, I just copy from the previous slide. This is from the previous slide, the complete ionic equation. From there, you can see, I mean, on the reactant side, there are 2 nitrate and 2 potassium ions. On the product side, we also have 2 potassium ions and 2 nitrate ions. So that means, okay, they can be canceled out, like the math, you know. If you do the sum equation in the math, if you have something on the left and on the right, they are identical, they can be canceled out, right? Similarly, here, the same principle, we can cancel out these common things on the both sides. And what left over will be lead ion, iodide ion, and lead iodide compound. So exactly I wrote down here. This is left over after we canceled out the common atoms. So this we give them a name called net ionic equation. I think net is a very good word. Tell you some common things are already deleted and this net left over. And in this case, we call the nitrate and the potassium ions are spectator. We'll talk about that later. Because these 2 ions, they remain in the same form before the reaction and after reaction. Seems they are just the same. They did not do anything. They did not contribute anything to this reaction. So they're just standing there and watch. This is why we call them spectator. So this is ionic, net ionic equation. So from the previous example, you know, this is a molecular equation. Yeah, this one. Yeah, everything is in the molecular form. And we can certainly write that equation into the ionic, first complete ionic equation before reaction. As you can see here, and let me see, am I recording? Let me see, I hope I'm recording. Maybe I did not record, huh? Okay, I will stop here.